Thanks, Nicola. I won't be offended. It's okay. So thanks for coming. So basically, I'm going to discuss some of the crazy ideas that we've been cooking up in the lab, and it's a little bit esoteric, so bear with me. So basically, what we're very, very curious about is, let me just figure this out. There you go. We're interested in how the brain is organized across different species. So if we kind of step back a little bit and look at what we have found for how the brain is organized, evolutionary sense, the easiest way is to compare neuroanatomy, right? We know this in so much detail that the human brain is significantly bigger than our primate relatives, for example. But more and more evidence has been found that it's not just the increase in brain size. There is also some disproportionate increases, say, in association areas, and so on and so forth. However, despite the differences between our common relatives, we know that there is some consistent large-scale organization in the brain. So we kind of need to step back a little bit and kind of find ways to explain why, even though we have these differences, we also have these consistencies. So we have to kind of go back into how the brain is organized. So the easiest way is, look at how areas and regions are defined in the brain. So the most typical way to do this is we assume that areas are distinct from its neighbors when we look at its homogeneity according to some structure, function, or connectivity. And this is what the previous speakers have been doing for the last, the last few speakers. So we know that this is the basis for how to define areas. So, and most of the data that we have are based on histological methodologies, trying to find landmarks based on architectonic profiles such as cytoarchitecture, myeloarchitecture, and chemoarchitecture. But there is some intrinsic problem here, right? If we use these unimodal features, we know that most of the time they won't produce consistent borders, right? And if we use, if we rely, for example, in one architectonic map, and we use that to represent how homogeneous it is in representing another brain feature, there might be some problem when you do that. And another potential problem is, say, if you look at the hedgehog brain and the tree shrew brain, functionally, there are homologous regions, but if you look at some architectonic landmarks, they actually have differences. So it's tricky to rely on these unimodal features. So I'm a human brain imaging person. How do we kind of use this information in defining areas in the human brain? Obviously, over the last several years, because of the advancements of MRI, we can now use different features at once or even at the same time. So say the Human Connectome Project Atlas, where you use multimodal features on myelination and structure and so on and so forth, or the Brainatome Atlas using structural functional connectivity all at once, we can kind of avoid those problems of using or of relying on unimodal features. But there is always a problem. That's why we do science. We always need to ask, right, like which feature is actually most transferable? Because again, if we compare all these 30, 40, 50 different parcellations in the human brain, you will always still find inconsistencies in borders. And a lot of our analysis rely on these definitions of borders, like structural connectivity will be different if you use different parcellations. And we also rely on very, very sharp transitions in these brain features, but there are a lot of evidences that features kind of change gradually through space. And most of methodologies will provide you parcellations that are single resolution. Say again, the HCP Atlas, which has 108 regions per hemisphere. And probably this is the most, for me, an important issue. Because if we use multimodal data that is not available across species, then we have now difficulty in extending these methodologies because it's hard to acquire these different types of data. And finally, if most of the methodologies that we have use these data sets to descriptively provide you borders, but we probably need to step back and better understand why the areas arise in the first place. So this is kind of the question that we're trying to answer, but obviously I don't know the answers to all of these, but we're trying to find ways to approach these challenges. One way, and this is a shameless plug, obviously, is to find a very, very common feature of the brain, and that's its geometry. All species will have the same feature in terms of its geometry. And what we found in our recent work is that if we use brain geometry and calculate what we call as the eigenmodes of the brain geometry, or these resonances, it kind of is a powerful methodology to parsimoniously represent emerging dynamics. So it provides you this interplay of structure and function that goes hand in hand. So the ultimate question that we're trying to do is, can we use these geometric constraints to provide some insights into how regions develop in the first place? So we're more curious on the process than defining the regions in these different types of mammalian brains that we're studying. So I'm just going to describe you a little bit of what the approach is, but I'm not going to go much into detail. You can chat with me in the poster hall later on. So basically, the only thing that we need is T1-weighted MRI, because we only need geometry. And you can run any of your favorite methodology to kind of approximate the cortical surface. But we can also do this in volumetric space, so you can just use a particular mask if you want to. And we calculate what we call the eigenmodes using this equation. But basically, this operator in here is the one that defines the spatial relationships between points in that cortical surface. So the approach is really, really simple. So again, you use the cortical surface as your input. We calculate what we call the eigenmodes. And here I'm showing you the first non-constant one, which is defining the anterior-posterior kind of variation. And we use the nodal line as an approximation of that separation. And then how do we move further on? We just iterate this process many, many times. So you can do this, divide the brain into two, and apply the same methodology to divide the brain further on. And obviously, what you will get in here is a division of the whole brain into two, which will divide into two. So you'll get powers of two of regions. But we've devised a way to use what we call the eigenvalues, which is basically the dominance of that eigenmode division, to split them according to the profile of the eigenvalues. And now you can follow this ordering to give you as many number of parcels and scale as you want. So we've done that for surface-based input, like the human cortex, and you can create as many parcels as you want. And because it's so simple and you only need the cortical surface, we can apply this to multiple species as well, like the macaques and the marmosets. And you can define an appropriate scale according to the question of your interest. Obviously, we don't have ground truth for these regions, right? So the only way for us to validate how good these parcellations are if we compare them to existing ones. So how do we do that? So we say we take the Brodmann map for the human cortex, which has 39 regions per hemisphere, and we create a counterpart of that with the same number of regions. Obviously, you can see that the regions are kind of look very, very different. But to be able to compare it comprehensively, we compare it to a lot more different parcellations existing in the human brain. And we also do that for the macaque and the marmosets. I grabbed as many of these parcellations as possible. And then we ask how homogeneous the regions are based on this geometric approach. So we use various data sets in the human brain, about 245 of those, and in macaques as well and marmosets, and we ask how homogeneous the parcellation is simultaneously. So it's not just functional homogeneity, how homogeneous it is across all these different types of modalities. So what did we find? So based, say, for functional connectivity homogeneity, we're seeing that the geometric parcellations are actually more homogeneous than its counterpart. say here, the red one. And we see the same consistent effect, oops, there's something wrong, across the different parcellations. And if we extend that to all the different types of modalities, we see the same effect. So here I'm showing you in the rows the parcellation and the different maps that we have. And red means the geometric parcellation is doing much better. And we see the same effect across the different maps simultaneously. And so it's better than about 70% of the maps relative to 17 of almost 18 of parcellations we've assessed. And we see the same effect in marmosets and macaques. So that's pretty much the method. So just to summarize, because I have limited time, I have 40 seconds, I think. I think I'm over time. So we've defined a new geometric approach for brain parcellation that is highly simple and just derived from T1 weighted MRI that produces highly homogeneous regions across diverse properties. But I have to emphasize that, again, we're not trying to define new regions. We're trying to define the process on how these regions emerge. And if you need more information, we can go to my post later on, and I'm presenting kind of similar thing in our symposium later, where we try to generalize this approach to more brain structures, more species, to multiple individuals, and kind of give you some kind of morphogenetic mechanism to describe this process further on. So thanks to all the people who have been involved in this work, and just a shameless plug for Ashley, there is this conference in September that people can attend if you're interested in evolution and development. So thank you very much.
Thank you. That's clearly a lot of work you put in there. I was wondering about the impact of variability between individual brains. Is that in any way captured in your parcellations?
Yeah, we can highly individualize the brain parcellations because it really follows the different sulci and the gyri and the folding. So we're trying to assess now how if you create functional connectivity, how does it differ? But we're showing that you get more functionally homogeneous regions if you do this individualization. But we're still carrying on that work. Yeah.
Time's up. We're moving on to the next speaker. Thank you.